If I ask you to solve this equation, it's really not tough. You combine the like terms right here, you get 5x minus 10 is equal to 25, and then after you add 10 to both sides and divide by 5, you're going to get that x is 7. There's a unique solution, and we know that because even though there's two variable terms, it's the same variable. So when you have an equation with just one unknown, one type of variable, you can solve and get a unique value. That's important when we're solving system of equations using substitution method or elimination method. Now let's look at it here. We got to solve the system. There's two lines, there's two equations, and we have to find the one ordered pair solution that will make both equations true simultaneously. And we're going to be using the substitution method. So here's what we have. We know that y is equal to 2x. That means in any ordered pair, whatever x is, the y has to be exactly twice as much. But this equation has a different relationship between x and y. If we were to subtract 3x from both sides in this one, then we'd know that y would be whatever 25 minus 3x would be. So that's all weird and crazy, but we don't have to get too bent out of shape with that. Let's make it simple. Here's the deal. We need this equation to affect this equation. And the way that we're going to solve this thing is to say, look, wherever we see the y down here, let's replace it with this 2x because they're equivalent to each other. Y has to equal 2x, so down here, let's let y be 2x. And in making this substitution, we can rewrite the second equation so it now becomes 3x plus this y is replaced by the 2x equals 25. A few really important things happen. Like we just got done saying, now we have one equation with one unknown, one type of variable. We'll be able to solve that equation and figure out that x must equal 5. The other important thing it does by substituting the 2x in for y here is it takes the information from the first equation and embeds it into the second equation so that both equations are working in tandem in order to find the ordered pair solution. So once we make this substitution, we get that x equals 5. We are halfway there. We know that our ordered pair solution for both equations has to have 5 as its x coordinate. Well, we know if this equation holds true, then the y has to be double whatever the x is, so this has to be 10. Literally what we do now is make another substitution back in for x. This guy becomes 5, so y must be 2 times 5, which is 10. There it is. That ordered pair will be a solution to this equation, and it will also be true that if we put 5 in here for the x and 10 in here from the y, we'll get 15 plus 10, and that is equal to 25. We've got our solution. Let's try this one. Solve this equation. We now see that x is by itself. X is defined by being 3y minus 1. So we're going to take the information from this equation and we're going to embed it in this equation down here. Wherever we see the x down here, we can replace it with its equivalent expression, which is 3y minus 1. Once we do that, write this second equation now, we get 2 times the substitution of 3y minus 1 plus the 3y is equal to 34. Now a nice thing happens. Once again, we just created an equation that has one unknown, only one type of variable. That's why we can actually solve it and get a numerical value. And the first equation is contributing to the second, so it'll be a solution that makes both equations true. So let's use the distributive property. 2 times 3y is 6y, 2 times this is minus 2, plus 3y has to equal 34. We can add the 2 to both sides and get 36. We can combine the like terms and get 9y equals 36. Dividing by y, or dividing by 9 rather, we get that y is equal to 4. We're halfway there. We know that the ordered pair solution must have as its y coordinate the number 4. Now, what is x going to be? Easiest thing to do, take this value and substitute back in for y in this original equation, because as soon as we evaluate that expression, we'll know the value of x. So we put a 4 right here. Put the 4 in for y. 3 times 4 is 12, minus 1 is 11. We now know that x is 11. That's the ordered pair solution for both equations. Now we have this. Now, most of us that have gone ahead and we've studied the elimination method, I like the elimination method for solving this, and we'll learn that in the next video, but we can do the substitution method. We just need to get a variable by itself. of the 4 variable terms, that's the one that has a coefficient of 1. It's easy to get this by itself by subtracting 3x from both sides. That converts this equation into y equals 7 minus 3x. So what do we now have? We now have y defined by x. Y is a function of x. That's what it means. So wherever we see a y, we can replace it with this right here. So we now take this into the second equation so that the first equation will have an impact on the second equation, and where we see the y, we'll replace it with that has an x term in it. We create an equation with one variable. So this becomes 4x plus 3 times the quantity, 7 minus 3x. That has to equal 6. Now we just do the math on this. Distribute the 3, we get 21 minus 9x. You still have the 4x over here. We can combine the two like terms, the negative 9x and the 4x. So 4x plus negative 9x is a negative 5x. We can get rid of the 21 and send it to the other side. So we'll take 21 away from both sides. So it must be true that negative 5x is equal to negative 15. We divide both sides by a negative 5, and our final answer is that x is going to be equal to 3. We now know that the x-coordinate of our one-ordered pair solution to both equations has to be 3 because both equations contributed to getting this value. Once we know that x is 3, we can now take this information, put it back up here, and we can know that y will be 7 minus 3 times 3. Well, 3 times 3 is 9, so 7 minus that 9 is going to be negative 2. There's our ordered pair solution to the system. So there it is, the substitution method. Get a variable by itself, substitute it into the other equation. You get an equation with just one variable term in it. Ding, solve it, and you're halfway there. Substitute back in, and bingo, you've got the solution to the system. Good luck.